Okay, in this video I'm going to begin exercise 5A of the book Fundamental Applied Mathematics. We're on page number 117 and the question is 1. It reads, a car has mass 1000 kilos. Its engine produces attractive effort or driving force of 2500 newtons. There is a resistance to motion of magnitude 500 newtons. The car starts from rest and we're asked to find its acceleration and distance travelled after 20 seconds. So the first thing we do is we draw a free body diagram, and that's a diagram depicting all the forces. So I'm going to let this rectangle equal to my car, or represent at least my car. So we're told there is a driving force, so I'm going to say that it is going in the positive I direction, and I'm going to call it D, whose magnitude is equal to 2500 units. Therefore the D vector is equal to positive 2500 I hat. Next we have a resistive force, and I'm going to call it R. So the magnitude of R is equal to 500 units, and the distance, or excuse me, its vector, so R is equal to negative 500 I hat. Now the question is, first of all, are these two vectors action-reaction pairs or Newton's third law pairs? And the answer is no. Now why is this? Well, the first one will be, this is going to be, we'll say it's a frictional force, and this is a driving force. So first of all, the driving force is being made by an engine. Alright, so there's going to be a force of the engine on the car, which is going to be a reaction pair with the force of the, why did I write G? The car on the engine. Now, we don't have an engine in this, we're just talking about the car. So for that reason, D here corresponds by the force of the engine on the car, but we're not dealing with this reaction pair, so or this vector as well. So we don't have a Newton's third law action-reaction pair here. And similarly over here, you might have like the reaction of the friction on the person and the person on the ground, but we don't. That doesn't apply here because we're not talking about the ground as well. The next thing is we're told that the mass of the particle is 500 or 1000 kilos. So we know, of course, from Newton's second law that F is equal to ma. Alright, so the mass of this is 1000 kilos. So the next question we need to ask ourselves is there an acceleration? And I'm going to tell you that there is, because we have a gravity vector which goes in the negative j direction. So we have its mass times its acceleration, which is negative 9.81, like so. Therefore the force is equal to negative 981 units, j hat like that, and it's newtons. Alright, so that is the force, and that force is called the weight vector. Alright, so that is in the j hat direction, of course. So let's just draw that in. We have a weight vector here. The weight vector is equal to 981, or the magnitude of which is 981, and its direction is 981 j hat, like so. So the question is, well, what is its reaction pair here? So what we've just found is the force of the car on the earth, and we need to find the force of the earth on the car. Okay, so it's a Newton's third law action-reaction pair. So it must be in the opposite direction, which is this way, and magnitude must be the same. So that means we call it the normal, by the way. The normal, its magnitude is equal to 981 units. Alright, and n is equal to 981 j hat, like so. And that is an action-reaction pair. Now, just to speak a bit more about the normal force, if I draw a horizontal and a vertical here, and I draw a ladder, okay, so here's my ladder, and it has two contact points, namely against the horizontal and against the vertical. And I'm going to tell you where there are contact points. You have the force of the ladder on the wall, which is going this direction, and we have to have a Newton's third law pair. So it's the force of the wall on the ladder. That is a Newton's third law action-reaction pair. Secondly, you also have, and I'm going to draw this in green, you have the weight of the ladder. Now that acts through the center, but it is a vector, so I can move it down here, and as a result we're going to have a Newton's third law pair here. So we're going to have the force of the ladder on the earth, and the force of the earth on the ladder. And these are action-reaction pairs, and that's what we have in this case. So remember, where there are contact points, you have an action-reaction pair, or a normal, and the normal is always perpendicular to the surface. Alright? So Newton's second law says that the sum of the forces is equal to the mass times the acceleration. So what are the sum of the forces? So let's just write them all down. So we get negative 500 I hat, positive 2500 I hat, negative 981 j hat, positive 981 j hat, like so. Alright, at this case, at this stage we're well able to do vectors. So we have the following: 2500 minus 500 I hat plus 981 minus 981 j. And that's going to be equal to 500 I hat plus 0j. Alright? Oh, not 500, excuse me, 2000, what am I saying? That's 2000. Like so. Alright? Now, let's just rewrite that. What that means is that the overall effect of all of these vectors here is the same as having my car and applying a vector of the magnitude. We're going to say that the force magnitude is equal to 2000, and where the force vector is equal to positive 2000 I hat. That's the overall effect of all those vectors. Alright? Now the next thing we need to do is work out what acceleration that has on the car. Remember, Newton's second law states that the sum of the forces is equal to the mass times acceleration. And that means if there's a force, there must be an acceleration. Similarly, if there is an acceleration, there must be a force. So what is our acceleration? So the sum of the forces is equal to 2000 is equal to the mass, which is 1000, times the acceleration. Therefore the acceleration is 2 meters per second squared. What am I doing here? Like that. Acceleration is 2 meters per second squared. Alright? So that was pretty straightforward. The last thing we need to do is just to work out the distance travelled by the car. So that's very straightforward. We're just looking at chapter 2 UVAST. We're told the car starts from rest. The time is 20 seconds and the acceleration is 2. So we're just going to use v is equal to u plus at. So it's going to be 0 plus 2 times 20. So v is equal to 40 meters per second. And to get the distance, I'm going to go s is equal to ut plus a half at squared. So s is equal to 0 times 20 plus a half 2 times 20 squared. So these cancel. So we just get 20 squared. So s is equal to 400 meters. Alright, so I'm just going to check this in the back of the book for our answer. So 5a question 1. Both of those are correct, so thanks for watching. Please pass it on to your friends and subscribe to my channel.